Welcome to this tutorial on hypothesis testing. Before viewing this tutorial, you should already be familiar with the concepts of creating confidence intervals around a population parameter. Essentially, hypothesis testing is an extension of confidence interval estimation. In this tutorial, we will discuss how hypothesis testing can help us to determine if we believe the true population parameter exists within an interval that we created. To begin, we start by making certain assumptions about the true population parameter, usually mu, the population mean, or p, the proportion population parameter. These assumptions we make are called hypotheses, and we begin by stating the null hypothesis and the alternative or research hypothesis. The notation for the null hypothesis looks like this: a capital H with a subscript of 0, which is called H naught. The naught referring to the null or subscript of 0, H naught. The alternative hypothesis is opposite or counter to the null hypothesis, and it looks like this: a capital H with a subscript of A. Sometimes we will have more than one hypothesis, and therefore multiple HAs are needed. In this case, instead of using just HA, we might have H subscript 1, H subscript 2, H subscript 3, and so on. But for the purposes of this tutorial, we will be concerned with only one null and one alternative hypothesis. So H naught and HA are sufficient for our purposes. Understanding how to formulate the null and alternative hypotheses is the first step in conducting a hypothesis test. If the hypotheses are not formulated correctly, then the researcher may not get the results he is looking for. The basic steps in hypothesis testing are to state the null and alternative hypothesis, then to take a sample, and use the sample results to provide evidence for rejecting or not rejecting the hypotheses, which leads to certain conclusions about the problem being studied. As you can see, the steps all culminate in a conclusion. So if the foundation, the formulation of the null and alternative hypothesis, is not solid, then the subsequent steps may lead to conclusions that are not helpful in solving the research problem. The first step, to state the null and alternative hypothesis, is actually a two-part process. First, we state the null hypothesis, which is an assumption about the true population parameter, usually either mu, the population mean, or p, the population proportion. The alternative hypothesis is then counter to that, or opposite the null. So for example, let's say we would like to determine if the light bulbs from a particular manufacturer burn an average of 1,050 hours. We would state the null hypothesis as H naught colon mu is equal to 1,050. This is our null hypothesis. This is our stated assumption. Then our alternative hypothesis would be counter or opposite to that. It is written as H subscript A colon mu not equal to 1,050. So we have two hypotheses here: the null with mu equal to 1,050 hours, and the alternative, sometimes called the research hypothesis, counter to that, so not equal to 1,050 hours. Our next step would be to take a sample of light bulbs. So let's say we take a sample of n equal 50 light bulbs, and we get a sample mean of x bar equal to 1,055 hours. Does this sample prove to us or give us evidence that the true mean is not equal to 1,050 hours? Or is it close enough to the true mean for us to believe that the mean might be 1,050 hours? What if the sample gave us an x bar of 1,070 hours? Is that enough evidence for us to reject the null hypothesis? And if we reject the null hypothesis, then that implies that there is enough evidence to support the alternative hypothesis. Now let's see how we would go about formulating the null and alternative hypothesis. We usually begin by looking at some claim or assertion about a population parameter. This is usually mu, the population mean, or p, the population proportion. So for example, we might say that if the manufacturing process is working properly, the mean number of hours the light bulb burns is 1,050 hours and no corrective action is necessary. In formulating hypotheses, the null is always one of the status quo, the way the process should be working. So if the manufacturing process is working properly, we should find an average burn time equal to 1050 hours. This is written as H naught colon mu is equal to 1050 hours. Now we're going to take a sample of light bulbs and test to see if there is evidence that the null is false. If it is false, then there must be an alternative hypothesis that is true. The alternative hypothesis is written opposite to the null hypothesis, and it would be stated as HA colon mu is not equal to 1050 hours. We already talked about the possible sample means we might get. We might get a sample mean of 1055 hours, and we might get a sample mean of 1070 hours. If the null hypothesis were true, then we would expect the sample mean to be close to the hypothesized mean of 1050 hours. So the closer the sample mean is to 1050, the less likely we are to reject the null hypothesis. The opposite is also true. The further away the sample mean is, the more likely we are to conclude that the true mean is not 1050 hours. The big question, of course, is how close is close enough, and how far is too far? And that is where hypothesis testing comes into play. But before we answer that question, let's take a look at another set of hypotheses. Let's say that instead of wanting to know the mean number of burn hours is equal to 1050, we want to know if the mean number of hours is at least 1050 hours. It stands to reason that the process is working fine if the light bulbs burn at least 1050 hours. That means 1050 hours or more. We don't have a problem if the bulbs last longer than 1050 hours. So in this case, the null hypothesis would be stated as follows. H naught colon mu is greater than or equal to 1050. That would be the status quo. Now notice the form of this null hypothesis. Instead of having an equal sign, it has a greater than or equal sign. So the alternative hypothesis, which is always written opposite or counter to the null, would look like this. HA colon mu is less than 1050. In general, we have three different forms that a hypothesis test can take when testing for the mean. The three forms look like this. We have a set of hypotheses with a greater than sign in the null, a set with a less than sign in the null, and a set with an equal to sign in the null. Let's look at each of these one by one. Starting on the left, let's look at the null that states mu is greater than or equal to mu naught. The mu naught would be some hypothesized value. So for our light bulb example, this would read as mu greater than or equal to 1050 hours. Now let's look at the alternative hypothesis. This is what we are looking to prove or find evidence for. So here we are looking to prove that the mean is less than 1050 hours. Now that means we would get a sample mean that is so low that we would have to conclude that there is evidence that the mean is less than the hypothesized value of 1050. If the true mean is really 1050, how could we get a sample mean that is 1030 hours? It's highly unlikely. So we would have to conclude that the true mean is not 1050 hours. Otherwise, we would not have gotten such a low sample mean. Take a look at this distribution on the right. Here we can see that the lower tail is marked off. If we get a sample mean that falls below this value, then we will no longer believe that the true mean is 1050 hours. And we will say that the evidence shows that the true mean is less than 1050 hours. Let's assume that the low value is a sample mean of 1030. As you can see, that is marked off on the lower tail, and this is why this type of test is called a one-tailed lower tail test. Since the area we are concerned about when the process is not working properly is the lower tail region. Now let's look at the set of hypotheses in the middle, and you can see that there is also a focus on a direction, but this time we are looking at the opposite direction, the upper tail area. Let's say we advertise a 10-minute oil change. The status quo or null hypothesis would be that the car's oil can be changed in 10 minutes or less. The alternative is that it takes greater than 10 minutes to change the oil, and we would take a sample to see how long it takes on average to service a car. If we get a sample average of, say, 13, then this might indicate that the true average cannot be 10 minutes. On the distribution, that would look like the way it's marked with 13 and the upper tail area marked off. Any sample results above that point would indicate evidence that the true mean is greater than the hypothesized value. This is called a one-tailed or upper tail test. And finally, we have the last case, which states a null and alternative hypothesis that doesn't focus on a direction. It is simply equal or not equal to. That means the process is not working properly if the sample data is either too high or too low. So there are two tails we are concerned about, both the upper tail and the lower tail, and therefore this is called a two-tailed test. Let's review what we have just discussed. First, we formulate our null and alternative hypotheses about a process or assumption about the population parameter. Then we go out and we collect a sample, and then we look for evidence in the sample that will help us to decide whether we reject the null hypothesis. And we can come to one of two conclusions: either reject the null hypothesis or do not reject the null hypothesis. Notice we do not say accept the null hypothesis, since this would imply that we have proven the null hypothesis to be true. We are not looking to prove the null hypothesis. We are looking for evidence to support the alternative hypothesis. That is why it is sometimes called the research hypothesis. Think about it this way. In a courtroom, the jury looks at evidence and decides if the defendant is guilty or not guilty. We never say the defendant is innocent, since that is not what we are looking for. There is a presumption of innocence, yes, but the jury's task is to look for evidence of guilt. If they find that evidence, then they pronounce guilty. If they don't find that evidence, then they don't say innocent, they say not guilty, meaning no evidence of guilt has been found. The same is true for hypothesis testing. We are looking for evidence of guilt, so to speak, evidence to support the alternative hypothesis. We either find it or we don't. If we don't find that evidence, then our conclusion is do not reject the null hypothesis, which is similar to the jury declaring not guilty. So the logic behind hypothesis testing is to gather evidence from a sample and see if we find enough evidence to conclude that the true mean is not what is stated in the null, which means we are looking for evidence that the alternative hypothesis is correct. In this sense, we are looking for the guilt that a jury is looking for. Back to our light bulb example. Let's say we want to test if there is evidence that the true mean is not 1050 hours. Then we would state our null hypothesis like this, and we would take a sample and look for evidence to see if the null is false. Our alternative hypothesis would look like this. That brings us to the critical value approach to hypothesis testing. Take a look at this distribution. It is marked off with areas of rejection and non-rejection regions. In the middle is the non-rejection region, and in the tail areas are the rejection regions. Earlier, we took a sample mean and we got 1055 hours. Now let's say we get a sample mean of 1051 hours. Well, then of course we would believe that the true mean is 1050 hours, since 1051 hours is so close to our hypothesized value of the mean. Now let's say we get some very, very high sample mean. Let's say we get a sample mean of 2000 hours. Now that's a really high number to get as a sample mean if the true mean was really only 1050. When the sample mean is so far away from the hypothesized population mean, then we will have to think that it is highly unlikely that the true mean is 1050 when we get such an outrageously high sample mean of 2000 hours. But here's the problem. Where is the point where the sample mean is too far away from the hypothesized mean that we no longer believe that it is true? Is it a sample mean of 1060, 1070, 1100, 1200? In other words, where is the cutoff point where we will no longer believe that the true mean is 1050 hours? In hypothesis testing, that cutoff point has a name, and it is called a critical value. We will mark it here and here. So now we have named the boundaries where the sample means are too far away from the hypothesized mean that we will no longer believe the true mean is 1050 hours. Those boundaries are marked by what is called a critical value. And if you recognize this from our previous discussion about confidence intervals, then you know that you will be looking this value up in the z table or the t table, depending on whether sigma is known or unknown. For now, let's understand that the distribution is divided into two regions, a non-rejection region in the middle and a rejection region. There are two rejection regions in this case since there are two tails and the tails are split between the upper tail and the lower tail. Now we said before that there are two conclusions we can come to when conducting a hypothesis test. If the sample values are close to 1050, then our first conclusion would be, do not reject the null hypothesis. That would mean that our sample statistic would fall within the non-rejection region between the two critical values here in the middle where the arrow is pointing. You can see that area is bounded by the two critical values. On the other hand, what happens if we get an outrageously large sample statistic or outrageously small? Then we would not believe that the true mean is 1050 hours and we would reject the null hypothesis. That would mean that our sample statistic is either too high or too low for us to believe the true mean is 1050 hours, and the sample statistic would fall in the rejection regions either above the critical value in the upper tail or below the critical value in the lower tail. Hypothesis testing provides us with a very powerful tool, but as we have discussed previously when we were talking about confidence intervals, alpha% of the time we will get a very low sample value even when the true mean is 1050 hours. It's just that we got a bad sample. And when we get a bad sample, it will cause us to reject the null hypothesis when in fact it is true and should not have been rejected. This will happen alpha% of the time. Remember, alpha is also called the level of significance. Alpha, or the level of significance, is the area in the tails, the area in the rejection regions. So if our level of significance is 0.05, then there is a 5% chance that we will get a very low sample or a very high sample statistic, even when the true mean is 1050 hours. So we can get bad samples that cause us to come to wrong conclusions. That is the nature of sampling. It happens. This is just one type of error we might make when we are doing hypothesis testing. In fact, when we conduct hypothesis testing, we can make two different types of errors. They are called type 1 and type 2 errors. Since the null and alternative hypotheses are opposing statements, one is written counter or opposite to the other, and they cannot both be true at the same time. Either the null hypothesis is true or the alternative hypothesis is true, but not both. Hopefully, our hypothesis testing will produce correct results, and we will not reject the null hypothesis when it is true, and we will reject it when it is false. But we don't always come to the correct conclusion. Sometimes we will get a sample that leads us to the wrong conclusion. For example, we may take the worst 50 light bulbs off the assembly line, and because they don't burn too long, we conclude that the true mean isn't 1050 hours, even though it really is. It's just that we took a bad sample. These types of errors, drawing the wrong conclusions, are illustrated in this table. This table shows the types of errors and conclusions that can be made in hypothesis testing. The first row of the table shows what will happen if our conclusion is, do not reject the null hypothesis. There are two scenarios. The null hypothesis may be true, and therefore we come to the correct conclusion, or the hypothesis may not be true, and we come to the wrong conclusion. In this case, we have made what is called a type 2 error. That is, we did not reject the null hypothesis when it was false and should have been rejected. The other type of error, a type 1 error, is the flip side of this. When we reject the null hypothesis and it should not have been rejected, then this is called a type 1 error. This will happen alpha% of the time. That is, we reject the null when it actually is true. This is also called the level of significance. So for example, if we choose a level of significance of say 0.05, then alpha is 0.05, and that is the probability of rejecting the null when it is true and should not have been rejected. On the other hand, if we reject the null and the alternative is true, then we did the right thing and we came to the right conclusion. When we are conducting research, we specify our level of significance, which is alpha, so we are controlling for the probability of making a type 1 error. We do not control for a type 2 error, and that is the reason why we never say accept the null hypothesis, but instead we say do not reject the null hypothesis. Controlling for a type 2 error can be done, but it is not common. So now let's take a look at how hypothesis testing is actually done. We will start with a hypothesis test for the population mean, sigma known. Now remember, we said we can conduct either a one-tailed test or a two-tailed test of significance. So let's start first with a two-tailed test. Let's say the manufacturer of light bulbs wants to determine whether his light bulbs last for 1,050 hours, so that he can claim that on the packaging. Since the manufacturer is testing to see if the mean is equal to 1,050 hours, and the counter or opposing hypothesis would be that the mean is not equal to 1,050 hours, then the hypotheses would be written as H naught mu is equal to 1,050 hours, and HA mu not equal to 1,050 hours. This is an example of a two-tailed test. Since there is no focus on a direction of greater than or less than, it is simply equal to or not equal to. Whenever the hypotheses are stated as equal or not equal to, then it is considered a two-tailed test. Now let's say we take a sample of 50 light bulbs, and sigma, the population standard deviation, is known to be 65, and let's say the sample produces a sample mean of 1,045 hours. The first step we have already done, that is to state the null and alternative hypotheses. Remember, the null is developed under the assumption the process is working properly, so the null is that the mean is 1,050 hours. The alternative is then counter or opposite to that the mean is not equal to 1,050 hours. Now here is the question. Does the sample mean of 1,045 hours provide enough evidence to reject the null hypothesis? The next step in hypothesis testing is to calculate the test statistic. That will be used to determine the difference between the sample mean x bar and the hypothesized value of the population mean mu. The test statistic for the mean when sigma is known should be familiar to you. It looks like this. Z is equal to x bar minus mu divided by sigma over the square root of n. Now we have a little not sign there in the mu because it isn't just mu, it is mu naught, which means the hypothesized value of the mean. So let's calculate the test statistic, and it is Z is equal to 1,045 minus the hypothesized value of the mean, which is 1,050, divided by 65 over the square root of n, which is 50. And we get negative 0.5441. The next step is to look up the critical value that will divide the normal distribution curve into rejection and non-rejection areas. This is what the distribution would look like with the areas divided into rejection and non-rejection regions. Before we can see where the boundaries are for the rejection and non-rejection regions, we must first specify alpha, our level of significance. Let's say we will be using an alpha value of 0.05. This is our level of significance. Since the rejection region is divided into two tails, remember this is a two-tailed test, we need to split alpha in half, so alpha divided in half is 0.025. Looking this value up in the Z table, we would get 1.96. This value, plus and minus 1.96, is called a critical value and marks off the boundaries separating the rejection region and the non-rejection regions. Our next step is to look at the test statistic and compare it with the critical value. Remember, we calculated our test statistic as negative 0.5441 on the previous slide. Now what is left is to compare the test statistic with the critical value. Does it fall in the rejection region or the non-rejection region? We'll take a look. The critical value is negative 1.96 at the lower tail and positive 1.96 at the upper tail. The test statistic falls in between these two critical values, so it falls somewhere around here, but clearly in the non-rejection region. Think of the critical value as a cutoff point or a boundary, and then see where the test statistic falls in comparison to those critical values. So for this example, the test statistic is in between the two cutoff points, or the two critical values, and therefore in the non-rejection region. Now we need to decide on our statistical decision whether to reject or not reject the null hypothesis. By comparing the test statistic to the critical value and seeing that it falls in the non-rejection region, then our conclusion would be do not reject the null hypothesis. And the last step would be to phrase this conclusion in the context of the problem. So we would say, there is no evidence to conclude that the true mean is different from 1,050 hours. In other words, after taking a sample and conducting a hypothesis test, we did not find evidence for the alternative hypothesis that the mean is not equal to 1,050 hours. What we have just discussed is called the critical value approach to hypothesis testing. Using this approach, we calculate the test statistic, then look up a critical value in the z-table to compare whether the null hypothesis should be rejected or not rejected. Another approach to hypothesis testing is called the p-value approach. The p-value is used to determine whether the null hypothesis should be rejected. To use this approach, the value of the test statistic is used to determine the p-value. Remember, the value of the test statistic in either the lower tail or the upper tail would provide evidence to reject the null hypothesis. Our first step is to calculate the test statistic. We already did this when we used the critical value approach. The test statistic was negative 0.5441. Now to find the p-value, we have to find the area under the curve to the left of negative 0.5441. Looking at the negative z-table, we need to find the area to the left of negative 0.5441 on the table. So we find negative 0.5 on the left and 0.04 at the top, and then following across and down, we get 0.2946. So 0.2946 is the area under the curve to the left of negative 0.5441. Now we double the p-value and compare it with alpha, the level of significance. We double the p-value since we have two tails, and we found 0.2946 in one tail, and since the distribution is symmetrical, then 0.2946 is also in the upper tail, and 0.2946 times 2 is 0.5892. Let's use a level of significance of 0.05, and now the rule is as follows. The rule for a p-value approach is to reject the null if the p-value is less than or equal to alpha. Otherwise, do not reject the null hypothesis. So what is our p-value? It is 0.5892. And what is alpha? 0.05. So 0.5892 is greater than alpha, which is 0.05, and therefore our conclusion should be do not reject the null hypothesis. It is the same conclusion we came to using the critical value approach. In fact, you will always come to the same conclusion whether you use the critical value approach or the p-value approach. If you think about it, you will realize that we are really doing the same thing, but going about it backwards one way and forwards the other way. So of course you will come to the same conclusion. We typically use the critical value approach when we are conducting hypothesis testing by hand calculations, but when we use a computer program to conduct the hypothesis test for us, the program will give us a p-value, and then we will need to compare that with alpha to determine the statistical conclusion of whether to reject the null hypothesis or not. So therefore, we do not reject the null, and to put this in the context of the problem, we would say there is no evidence that the mean is different from 1,050 hours. Now let's see how we would conduct a one-tail test using the critical value approach and the p-value approach. In this example, the department claims that the mean grade on an exam was at least a 65. Suppose we want to test if there is evidence that the true mean is lower than claimed. We take a sample of 75 students and obtain a sample mean of 60, and from historical data we know that the population standard deviation is 15 points. The sample mean is 60, which is below a 65, but the question is that enough evidence for us to conclude that the true mean is less than 65? So first let's state our null and alternative hypotheses. The null is the status quo, so that would be that the mean is 65 or greater. That is what the department claims is true, but it is the alternative hypothesis that we are looking to find evidence for. So in this case, since we are looking to see if there is evidence that the true mean is less than 65, the alternative hypothesis is that the mean is mu is less than 65. Sometimes it is easier to first formulate the alternative hypothesis by looking to see what we are trying to prove and then write the null counter or opposite to that. But when it is written formally, the null is shown first and then the alternative hypothesis. Remember, the alternative hypothesis is also called the research hypothesis. So that is what we are always looking to prove or find evidence for. Now we can conduct our hypothesis test, and it is done in much the same way as when we conducted a two-tail test, except that now we have only one tail or one area of rejection. And which tail would that be? It is always the direction of the alternative or research hypothesis. So here in the alternative hypothesis, it says less than 65. So we are focusing on the less than or lower tail region. This is our rejection region, and if the test statistic falls in this region, our conclusion will be to reject the null, and that is that we have found evidence to support the alternative hypothesis. And then the entire region to the right of that area is the non-rejection region. Now, using the critical value approach, we need to calculate the test statistic and look up the critical value for a specified alpha value, and then compare the two to come to a statistical conclusion. So let's do that. To calculate the test statistic for a one-tail test, we use the same formula as we did for a two-tail test. Z is equal to x bar minus mu naught divided by sigma over the square root of n. In fact, almost everything we did for a two-tail test, we do for a one-tail test. There are only minor differences, such as the way the null and alternative hypotheses are stated, and the rejection region is only in one tail area and not two tails. So let's calculate the test statistic. 60 minus 65 divided by 15 over the square root of 75. And that gives us minus 2.8867. The next step in hypothesis testing using the critical value approach is to look up the critical value. Let's say we decide to use a 0.05 level of significance, that is alpha 0.05. This level of significance is something we as the researcher chooses depending on the level of confidence desired. Remember, the alpha value is also the probability of making a type 1 error, that is rejecting the null when it is in fact true and should not have been rejected. So let's say we choose 0.05 as a level of significance. Now let's look up our critical value in the z-table. Looking in the center of the table for 0.05, we see two values that are close to that, 0.0505 and 0.0495. 0.05 would be right in the middle of those two numbers. Now looking to the left, we see negative 1.6, and looking up, we see that 0.05 would be halfway between 0.04 and 0.05. So we get a critical value of negative 1.645. That is the value we're going to use as a cutoff point to compare our test statistic. That is our critical value. The next step is to compare the test statistic with the critical value and come to a statistical conclusion. Well, let's see where the test statistic falls. Here is the distribution with the lower tail area marked off at the critical value point we just looked up, minus 1.645, and the test statistic was calculated as negative 2.8867. So on the distribution, that would be around here. Remember, the tail areas are the areas of rejection, and the test statistic is in the rejection region. So our conclusion would be to reject the null hypothesis and find that there is evidence to support the alternative hypothesis that the mean grade is less than 65. What we just did was a hypothesis test using the critical value approach. Now let's see how this could be done using the p-value approach. The result, of course, will be the same, but the process is just a little different. Remember, we did this a couple slides back for the two-tail test. The p-value approach uses the test statistic to compute the p-value, and then that p-value is compared with alpha. The rejection rule is as follows. We will reject the null hypothesis if the p-value is less than or equal to the alpha value. For our example, we calculated a test statistic of negative 2.8867, and we stipulated a 0.05 level of significance. So using the z-table, we look up negative 2.8867. Looking on the left, we find negative 2.8, and on top, let's use 0.09, and we get a p-value of 0.0019. That would be the area under the curve in the lower tail below a z-value of 2.89. So now that we found the p-value of 0.0019, the next step is to compare it with alpha. Take a look at the rejection rule. It says that we should reject the null hypothesis if the p-value is less than alpha. Is it? Yes, 0.0019 is less than 0.05, and therefore we reject the null hypothesis and find evidence for the alternative hypothesis that the true mean grade is less than 65. That concludes this introductory tutorial to hypothesis testing. Please make sure to watch the continuation of this tutorial, part 2, where we conduct hypothesis testing for the case of sigma unknown, and part 3, where we conduct hypothesis testing for proportions.